Okay, so I have a confession to make. Actually, when I ended the previous video, uh, actually I wanted to pause the video, but I pressed the wrong button and I ended the wrong video. Yeah, I mean I ended the video wrongly, and I think now I'm going to post two separate videos because I'm not going to edit a 20-minute video. I'm not gonna like merge two 20-minute videos together. It will like ruin my storage, man, and not to mention it will take very long to like download into my iPad. Okay, so um I guess I guess I'll just make this like a separate YouTube video, but it's basically the same thing, guys. This is just a continuation from the previous video which we were talking about the properties of ionic and covalent compounds. Okay, so where we left off was at the crystalline structure part. So I'm going to show you the structure of a quartz. Okay, you look at this quartz and you tell me, I mean like, I mean like, okay. So what you can tell from this is that it is very neat and orderly organized to the point that we can identify its shape, where the edges are very defined, where it has sharp corners, and all the okay. Yeah, let's look for lattice, the word lattice. Okay, and it is a repetitive structure. From this picture, it is basically like the same layer copy and pasted, and they are put right beside each other. So this is like a crystalline structure. Okay, I'm gonna pause now and I'll go back to my pad. Oh wait, what? Okay, am I recording? Okay, yeah, I'm recording. Okay, we're going back to our uh, notes. Okay, so ionic is basically crystalline solids. Okay, and we're gonna have to remember this to no, we're going to remember this to understand the upcoming what upcoming to understand the other physical properties of ionic compounds. Okay, so you know what? Let's just go ionic all the way. Okay, so since they have crystalline solids, um, okay, since they have um, okay, no, it's not. I wouldn't say that because of being a solid, it has high melting point, but it is somewhat related. Okay, never mind. So the melting and boiling point is high, high MP and BP. The arrow, this is an arrow, by the way. Oh my god, that is such an ugly arrow. Oh, someone's phone vibrating. Okay, you get the idea. Wait, hold on. Let me. Okay, never mind. It's gone. Okay. So, it has a high melting and boiling point. And, um, let me explain why. Okay? So, go back to the dot and cross diagram of an ionic bond. It's basically this minus charge and this a positive charge. I don't know why I draw the bracket so big. I just did it. Okay? So, the negative and the positive charge, um, they all add up, right? As in like, it's either -1 and +1, or it's like, let's say -2 and then it's +1 +1, right? So they will always add up to 0, or in some cases it's -3 +1 +1 +1, right? So it will always add up to 0. So this negative and positive charge, um, we call it the elect electrostatic forces. Okay, let me write it. Electro as in electric, electrostatic as in the Steve Lacy song. Ha ha ha. Yes. Electrostatic forces of attraction. Electrostatic forces of electrostatic forces of attraction. Okay, so the key word here is electrostatic. Okay, one way to remember, there's actually another word, but it's for covalent compounds. It's called intermolecular. Oh my god, wait. Intermolecular forces of attraction. But electrostatic is specially for ionic. One way to remember which word is for which compound is by, electro, and there's charge. Oh my god. Okay. So charge is basically like a physics term, but to very 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 simplify it, charge is basically electricity. It's basically related to electricity. Okay, so one way to remember is electrostatic and there's a charge. Alright, so what about these electrostatic forces of attraction? Well, the electrostatic forces of attraction are really 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 high. It's a very strong electrostatic force of attraction. These electrostatic forces of attraction, right, they are so strong that this negatively charged atom and this positively charged atom, they will come together and they will not budge. So again, in physics we learn the law of attraction, which I think you would have learned in lower sec and even maybe primary school. It is like poles repel, unlike poles attract. So we apply that same kind of logic, but instead of like the north and south pole, it's instead the charge. So like charges repel, unlike charges attract. And since this is negative and one is positive, they are unlike charges. And since they are unlike charges, they attract. And they are basically now hand in hand. But remember, they don't overlap. They're just hand in hand. They're like touching like that. They're basically touching. Okay, let me draw. Yep, they're touching. Okay, so these electrostatic forces of attraction, it keeps the atoms and the molecules in like this manner, right? So what happens when a substance melts or when it boils? So when a substance melts or boils, we learn that it gets further apart from one another, right? Oh wait, actually, when hold on. When it melts, it loses its orderly structure, but it's still like relatively close. Okay, so this is from solid go to a liquid. Okay, and then from liquid to a gas, it goes from this to that. So this gas. So you can see the trend here is ignore the size difference, it doesn't matter. So the trend here is that they are getting further apart, but in the very first place they were close together because the electrostatic forces of attraction were keeping them together, right? So the electrostatic forces of attraction, right, suddenly something happened to them to the point where that these friends, right, they were so close, now they drift apart already. They're not talking anymore. After they graduate, they're not talking anymore. Like some people I know. Okay, so what happened to these electrostatic forces of attraction? Well, basically, when you heat up a okay, let's imagine an ice cube. Okay, an ice cube. Okay, DNT skills are going okay. Yeah, cube. That's good enough. I think Haziq is the only one in this account that takes DNT. Don't judge my DNT drawing skills. Okay, so this is an ice cube, right? So we give it heat. Okay, let's be very funny here, and we give actual flame at the bottom of an ice cube. Okay. I want black. Black. Okay. Okay. So when the ice cube gains heat, right? The particles, the electrostatic forces of attraction, let's call it EFOA for short term. The EFOA, um, let's think. Well, okay, the it is obviously a force, right? The electrostatic forces. So it's a force, but then below here, there's a flame, and the flame, we all learn in lower sec, flame is heat. Wait, no, I want this to be purple. Okay, and this will be orange. Okay, so flame has heat, and heat is basically thermal energy, right? Okay, so this thermal energy, right, it breaks it okay doesn't break the electrical forces of attraction. um you know what would be a easier concept for you to understand? Okay, so thermal energy, I'll just short form TE. Okay, so there's this battle between the thermal energy and the electrostatic forces of attraction. Okay, and as it go and as the solents and as the substance goes from solid to liquid, there are as the substance goes from a solid to liquid, the temperature increases. It so the temperature, the thermal energy grows stronger, and because the thermal energy now grows stronger, the electrostatic forces of attraction is now weaker. So that's the whole physics behind the high melting and boiling point. However, yeah, okay, sorry, okay. So, how do okay, okay, so ionic compounds, right? Like what I said earlier, they have very strong electrostatic forces of attraction. Very strong. I put two arrows. Very strong forces of attraction. So to weaken this EFOA, what we need is a very strong amount or a very large amount of heat, or TE. Heat slash TE. Okay, we need even larger amounts of heat slash thermal energy. So therefore, it has a high melting and boiling point. You get what I mean? Okay, let me put it in another way. Okay, let's draw the temperature time graph. Okay, so this is the temperature and this is the time, which is seconds. Okay, so solid, then liquid, then gas. Okay, so this temperature would be, let's say, 95 degrees Celsius. Why? Because at this stage over here, the molecules, they still have a strong EFOA. So thus, when you give it, like, let's say 50 degrees Celsius of heat, it is still a solid. So it is very hard to make this substance go from a solid from a solid to a liquid, because the strong EFOA requires a lot of heat energy, a lot of thermal energy for it to be weakened, and it needs to be weakened to a point such that the EFOA can no longer hold these molecules together. So the heat and the thermal energy that has been like um exerted, oh no, so basically the heat, when I heat this substance until it is 100 degrees Celsius, the EFOA is weakened, is weak to the point that these molecules, they don't have anything holding them back anymore. So with nothing holding them back, they can start to move away from one another. But again, they need a lot of heat for them to move away. So that's why they have strong melting, high melting and boiling points. Whew, that was a long explanation. I think that took like 7 or 10 minutes. I just cause it's like it took me a while to understand, and I really wanted to like properly explain, but I didn't know how to properly explain. So yeah, that's my greatest weakness, I guess. I delete. IMP and BP. Okay. So next we'll talk about volatility. What is volatility? Okay. Vola eh yeah, volatility. Volatility. So what is the root word of volatility? It is volatile. Volatile. Okay, now let's Google what volatile means. Okay, so volatile. Volatile means a substance that easily evaporates at normal temperature. Okay, yeah, we look at the first explanation. Okay, the first explanation is easily evaporated at normal temperatures. The keyword is easily, easily, and normal temperatures. Okay, so go back to the. Okay, so back to what we previously learned. Ionic compounds have high melting and boiling points, and these melting and boiling points, they are way above the above the normal temperature. So since ionic compounds have high melting and boiling points, they would then have a low volatility, because they would not be able to evaporate easily. So that's the answer. They do not evaporate easily. Okay, next thing, we are gonna look at electrical conductivity. Electrical conductivity. Okay. So when ionic compounds are solids, they do not conduct electricity. However, when they are aqueous, is that the right spelling? Aqueous. Yes. However, when they are aqueous or when they are in a molten state, they can conduct electricity. Okay. So I'm just gonna assume that by now you should know what aqueous and molten substances are. Aqueous basically means that it has it has been dissolved in a solvent, and molten means it is like in like, just think of molten magma or molten lava. Okay, you get what I mean? It's basically melted in a melted form. Yeah. Okay. Okay. So again, let's go back to the chemical. No, let's go back to the dot and cross diagram. No, wait. Should we? Okay, yeah. Okay, fine. Whatever. So we have a plus, and so we have a plus and we have a minus. Okay. So again, we have the charge. Okay. Now let's backtrack a bit. What is the reason behind these atoms having a charge? That's right. Ions. What are ions again? What are ions? Okay, let me look at my notes. What are ions? Let's see. Does my notes say what ions are? It should say. I'm too lazy to find. Okay, basically, ions are electrons. Ions and electrons are kind of the same thing. And don't quote me on this because I don't want to get scolded for giving wrong information. But from what I have noticed, in chemistry we use the word ions, but in physics we use the word electrons. So I'm kind of guessing they are the same thing. Okay, remember back in the previous video, we learned that ions are formed when electrons are either lost or given. So no, I either lost or gained. Yeah. Okay. So this substance, this atom had given one electron to is it? No, it's the other way around. So this substance has given this substance one electron, right? So when it gives one electron like that, okay. Okay. You know what? Let's just stop it here. As in, like, let's stop the explanation here. So basically, just think of it as ions and electrons having ions and electrons being relatively the same thing. Okay. Okay. Now, okay. So when a substance is in a solid form, okay, solid. So when it's solid, it's neatly and orderly, and they are all shake in their vibrate about in their fixed position, so they cannot move. They all vibrate only. Okay, so that's why. Okay. Oh my god. Okay. Back to what we learned just now. At solids, they have high electrostatic forces of attraction. Right. Okay. So I wanna add on to that and say that these electrostatic forces of attraction, oh, they are so strong that not only do they keep these molecules together, but they also keep the electrons together. Okay, so now let's use light blue to represent electrons. So this is one molecule, right? I mean, this is one atom, right? So as we learned previously, in previous chapters, the electrons are not in the nucleus of the atom. Instead, they are like further apart. Right. So these are the electrons. They are all away from the nucleus, basically away from the center, a bit further away. Right. Okay. So these electrostatic forces of attraction, they keep these electrons somewhat like near the atoms. Basically they keep them at a specific spot, right? So it doesn't allow the electrons to go any like further. It doesn't allow the electrons to go here or go there, right? Because it keeps them, it really keeps them to be near the atoms. Okay, so that's in solid. So when these electrons are kept in a single section, a single section, a single part of an area, I don't know, basically these electrons cannot move far away. They can move about, maybe they can move about like within a radius there. They can move about freely in that circle, right? So since they cannot move about very freely, they cannot carry charges. And you're thinking, huh, what carry charges? Okay, so electrons, they can carry charges. Why? Because uh in the dot and cross diagram, there were plus and minus, right? So why do you think there was a plus and minus? Because the electrons move from one atom to another atom. What? So when it does that, it carries along their charge. And what is the charge of one electron? That's my favorite question. Charge of one electron is -1. So when an electron moves around, it carries a charge of it carries a charge of -1. Ah. So when it's in a solid form, when it's in a solid state, these electrons, they cannot carry their -1 charge anywhere. Maybe like a bit to the left, a bit to the right, a bit up here, a bit down here, maybe sideways also can. I mean diagonally also can, but not very far. Not very far to the extent that it can carry charge in a wire. You get what I mean? Okay, I mean, okay, ignore the wire part. Let me rephrase it. These electrons cannot carry charge throughout a medium. You get what I mean? Basically, these charges cannot carry. These electrons cannot carry these charges very far. Okay. 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 Let's now move on to aqueous and molten states. Okay. When they are in aqueous and molten states, basically either they are dissolved or they are melted. Let's draw the arrangement. So we have one here. Okay, wait. We have one here, maybe one here, one here, one here, and one here, one here also, and one here. Okay, okay. So now let's draw the electrons. Electrons are here, here, over 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 here. Okay. So right, let's go back to the strength of the electrostatic forces of attraction. Okay, the electrostatic forces of attraction, now that they are dissolved or molten, they would be lower as compared to the EFOA in solids. So right, when the EFOA is now weaker, what do you think will happen to the electrons? That's right, the electrons will now move further away from one another. Maybe because of diffusion, maybe because they don't like each other. That one I'm not really sure. Okay, so when they move up, they move away from each other, and this time the EFOA is weakened to the point where this electron can move here, and who knows, maybe over here there might be another atom, and or maybe over here also got another atom, and over here also got another atom, right? So when these charges travel that far from a charge being over here to maybe being over here, or maybe over here going to over here, cannot be inside, over here, over here, over here, over here, over here, so these electrons can travel far, right? So when they travel far, they also carry their negative one charge. So therefore, when it is aqueous or molten, it can carry a charge, thus being an electrical conductor, being a conductor of electricity when in an aqueous or molten state. Okay, so when the question asks you, explain blah blah blah, or like explain why this is so, okay, I would strongly suggest you to revise your notes lah, because this tuition or this video is mainly for you to like have a simple understanding of why things happen, or like just a recap. But I'll just put the explanation over here. Okay, I'll just put the important phrase that you need to know. Okay, so when they ask you to explain why ionic compounds can or cannot carry charges, you put it this way. So if it's in a solid form, you basically explain like okay, when it is in a solid form, there is an absence of mobile electrons. Due to that, the there are no free moving electrons to carry charges throughout the solid. If it's an aqueous or molten form, then you can say in an aqueous or molten form, there is a presence of mobile electrons. Thus, these free moving electrons, oh no, you cannot say electrons. Mobile, actually you can't even say mobile actually. I'm not sure. Why did my notes put mobile? Off. In chemistry, we say maybe in physics we would say mobile electrons. That's why. So in chemistry we say free moving ions. Basically the ions are free to move about and carry charges throughout the entire substance. Okay. Okay, and then solubility. How soluble it is. This one, to be honest, I'm also not certain about the way this works, but I mean, it's easy to remember. Okay. Okay, so it's soluble in water but insoluble in organic solvents. So what are organic solvents? Some example are petrol. Um, let's see what else is in my notes, my other notes. Oh no, I didn't sort this out. Okay, give me a minute. Did I not put ah ethanol? Ethanol is an example of an organic solvent. Ethanol. One way to remember is ethanol. My I had a classmate in Sec 2 whose name is Ethan. Okay. Oh, Ethan also takes pure science, so he would be more qualified for this. Okay, so now for the physical properties of covalent compounds, which is basically the complete opposite of ionic compounds. So this is a solid, right? Then this would be so this would usually be liquid. Okay, let me improve my handwriting. Liquid or gases at RTP. What is RTP again? Room temperature and pressure. Okay, and then it has low melting melting point and boiling point. Why? Okay. Okay, I need you to understand. This is a covalent bond. This is an intermolecular bond. Okay? Intermolecular bond. So this intermolecular bond is weak, lemah, and this covalent bond is strong. Okay, so let's dissect. Let's say let's say it's H2O, water, okay? Water. So H2O, okay? So the covalent bond between oxygen and hydrogen is strong. But the intermolecular bond between one circle is H2O. Okay, why? Okay, imagine ice when it melts. It melts easily, right? Because it has a low melting and boiling point. It has a low melting point. And ice is basically a bunch of H2O molecules together. Right? Okay. So, now you imagine you're boiling water. When you boil water, right, you get a gas. Is that gas steam or is that gas oxygen and hydrogen? I'll give you 10 seconds to answer. Steam or oxygen and hydrogen? Okay, I'll give you 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, the answer is steam. We learned this in PSLE. When we boil water, we get steam. And steam is basically H2O just in a gaseous form. What we don't get is pure oxygen or pure hydrogen. Why? Because when we apply heat, right, we apply heat here. We don't apply heat at this level. Do you get what I mean? Okay, come, let me draw a model. A very advanced model. There's a difference between intermolecular and covalent bonds, okay? And let me show you. Okay, H2O. Actually, you know what? I will use black. Okay, so when we apply heat over here, so that the blue circles will separate. One move here and one move there. Okay, what we don't get, or what doesn't happen, right, is oxygen go here and hydrogen go there. When hydrogen uh when hydrogen like breaks off from oxygen, we don't get that. Okay, only the blue circles move away, they break apart, because the bond here, we call it the intermolecular bond, right? The intermolecular bond itself is weak, lemah, but the covalent bond over here is strong. So that's why hydrogen and oxygen doesn't break apart. Okay, so you have to take note of that lah. I think I'm not gonna give like the model phrase, cause I think you can learn that on yourself lah. I'm just explaining like the important things to take note of. Okay, volatility. Since again opposite of ionic, and since it has a low melting point, it is very volatile. Okay, electrical conductivity, cannot conduct electricity at all. Whether it's aqueous, solid, molten, or gaseous, it cannot conduct electricity. Never ever. Okay. Oh, and then you might be thinking, wait, isn't water a covalent compound? And can't water conduct electricity? Well, my friend, I would like to refer to you to YouTube, because when you when you use pure water and legit pure water, you cannot conduct electricity. However, when you, let's say, you add table salt into this water, only then can you conduct electricity, because there are small tiny impurities in water that conduct electricity. And there's many videos on YouTube which show this, so you can search does pure water conduct electricity, or why doesn't pure water conduct electricity, on YouTube. Okay, this is 44 minutes long already. I'll just finish up with solubility, and is the complete opposite of ionic. So it's insoluble in water. I got no space. Alamak. Okay, I'll just say it's insoluble in water, whereas it's soluble in organic solvents. Good. The end. Okay, that's it. I am tired from talking non-stop for an hour. Okay. Just. Okay, yeah, that's it. Don't forget to like, share, subscribe, and comment down on any questions that you may still have, or comment down what other topics or even subjects I should cover on this type of tuition slash crash course. I plan to do acids and bases next, and then I will do neutralization and salts, and then after that I will do organic chemistry. I plan to do acids and bases and neutralization and salts either later or tomorrow, but I'll do it within this weekend. And then for organic chemistry, I'll do it later in the week, maybe Wednesday. Yeah, okay, that's it, my friends. I'm gonna take a long nap now and, yeah, recuperate and whatnot. Okay, goodbye, bye.